Two galaxies are going to collide. Not a hypothetical, not a distant scenario. The Milky Way, the galaxy containing the Sun, the Earth, and every star you have ever seen in the night sky, is on a collision course with the Andromeda galaxy. The collision will begin in approximately 4.5 billion years. It is gravitationally inevitable. Nothing in the solar system's future will change it. The Andromeda galaxy contains approximately 1 trillion stars. The Milky Way contains between 100 and 400 billion. When they meet, the combined stellar population of 2 trillion stars will interact gravitationally over hundreds of millions of years, producing a merger that will reshape both galaxies entirely. Now consider what the word collision means in this context. When two cars collide, metal contacts metal. The collision involves direct physical contact between material objects. When two ocean waves collide, water molecules interact directly. When two billiard balls collide, atomic forces between the surfaces produce the impact. When two galaxies collide, almost none of the stars make contact with any other star. This is not an approximation, not a simplification for general audiences. It is a precise statement about the geometry of galaxies. Stars are so small relative to the distances between them that two galaxies can pass completely through each other, all the stars of one galaxy moving through all the stars of the other, without a single stellar collision occurring. The collision of two galaxies is, in large part, empty space passing through empty space. And yet, something dramatic happens. Stars are ejected into intergalactic space. New stars form at rates far exceeding anything in the individual galaxies. The central black holes spiral toward each other and eventually merge. The entire structure of both galaxies is transformed into something neither of them was before. All of this happens without the stars actually touching. In this video, we are going to go through exactly what a galaxy merger is, why the stars do not collide, what the gravitational interactions actually do, and what the Milky Way-Andromeda merger will look like, from the first gravitational perturbations 4.5 billion years from now, to the final merged elliptical galaxy that will exist long after our sun has died. There is something in the fourth section of this video that most people find the most disorienting. Not the fact that the stars do not collide, but a specific calculation about the probability that the solar system will be significantly disturbed during the merger. The answer contradicts what most people assume when they first hear about the collision. Stay with me. The logic breaks in the first section. Before we go further, the Milky Way and Andromeda will collide in 4.5 billion years. Two galaxies, 2 trillion stars combined, and almost certainly 0 stellar collisions. Drop a comment with what you think actually happens to the stars if they do not physically collide. Most people get this wrong, and the right answer is more interesting than the obvious one. Let's start with the geometry, because the geometry of galaxies is profoundly counterintuitive. The Sun is approximately 1.4 million kilometers in diameter. The nearest star to the Sun, Proxima Centauri, is approximately 4.24 light-years away. 1 light-year is approximately 9.5 trillion kilometers. Proxima Centauri is approximately 40 trillion kilometers from the Sun. The ratio of the distance between stars to the size of a star is approximately 40 trillion divided by 1.4 million, approximately 28 million. If the Sun were the size of a marble, about 1 centimeter in diameter, the nearest star would be approximately 280 kilometers away. Imagine marbles separated by the distance from London to Berlin. That is how densely packed stars are in our galaxy. The Milky Way is a disk approximately 100,000 light-years in diameter and approximately 1,000 light-years thick. It contains between 100 and 400 billion stars. The average distance between stars in the disk, using 200 billion stars and the disk's volume as an estimate, is approximately 4 to 5 light-years. When the Milky Way and Andromeda merge, the stellar density in the combined system approximately doubles. The average distance between stars decreases by approximately the cube root of 2, a factor of about 1.26. Stars that were on average 4 light-years apart are now on average approximately 3.2 light-years apart. The probability that any two specific stars come within, say, 1 light-year of each other during the merger is extremely small. The probability that any stellar collision occurs at all, that two stars actually come close enough for their surfaces to interact, is calculated by integrating the collision cross-sections over the stellar density and relative velocity distribution during the merger. The calculation has been done. The result is that the expected number of direct stellar collisions during the Milky Way-Andromeda merger is essentially 0. Not 0 by approximation. 0 in the sense that the probability of even one stellar collision occurring anywhere in the merged system during the entire merger process is a small fraction. 2 galaxies, 2 trillion stars, hundreds of millions of years of interaction. No stellar collisions. The reason this works is simple geometry. Stars occupy an extraordinarily small fraction of the volume of a galaxy. A galaxy is not a dense collection of stars. It is an almost empty space in which stars are scattered with extraordinary sparsity. The collision is real. The merger is real. The transformation is real. But the mechanism is not physical contact between stars. It is gravity operating at distances measured in light-years. The probability of stellar collisions during galaxy mergers has been calculated in multiple n-body simulation studies. The 2008 Cox and Loeb paper in Monthly Notices of the Royal Astronomical Society, using a simulation of the Milky Way-Andromeda merger, found that the probability of the Sun being directly involved in a stellar encounter close enough to significantly perturb the solar system is approximately 3% during the merger. Direct stellar collisions, two stars making physical contact, were not found to occur in any of the simulated merger scenarios. The filling factor of stars in a galaxy, the fraction of the galaxy's volume actually occupied by stellar material, is approximately 10 to the negative 23. There is an analogy that makes the geometry concrete. Imagine firing 2 shotgun blasts at each other from a distance of a kilometer. Each shotgun fires 200 billion pellets. The pellets from the 2 blasts travel toward each other, pass through the same region of space, and continue out the other side. How many pellets collide with each other? The answer depends on how densely the pellets are packed in the blast pattern. If the pellets are spread over a large enough area, the probability of any 2 pellets from opposite blasts hitting each other is negligibly small. Most pellets simply pass through the gaps between the oncoming pellets. Galaxies are the pellets spread over an enormous area. The area is so large and the pellets so small that even 200 billion of them in each blast do not reliably collide with each other. What does happen to the pellets, to the stars, during this passage? They are gravitationally perturbed. Their trajectories are altered by the combined gravitational field of all the stars in both galaxies. They are pulled in new directions, accelerated, decelerated, ejected, captured. Gravity acts on everything. But it acts at distances measured in light years, not in meters. The collision is entirely gravitational. Not a single star needs to touch another star for the entire process to occur. Let's go through the timeline of the Milky Way-Andromeda merger, the sequence of events from the current approach to the final merged galaxy. Currently, Andromeda is approximately 2.5 million light-years from the Milky Way. It is approaching at approximately 110 kilometers per second along the line of sight, the radial velocity, and has a transverse velocity that is more uncertain but is estimated to be relatively small. The combination of these velocities and the gravitational attraction between the two galaxies makes a collision in approximately 4.5 billion years inevitable. The 4.5 billion year figure is not approximate in the sense of being uncertain by a factor of 2. It is uncertain by approximately 400 million years. The collision could occur anywhere from approximately 4.1 to 4.9 billion years from now. But the collision itself is not uncertain. It will happen. The uncertainty comes primarily from the poorly constrained transverse velocity of Andromeda. If Andromeda's transverse velocity is very small, the two galaxies will collide nearly head-on. If it is larger, the collision will be more of a glancing blow, and the merger will take longer. In approximately 2 billion years before the collision, the gravitational interaction between the two galaxies will become noticeable in the sky of any observer in the solar system. Andromeda, currently a faint oval of light visible to the naked eye under dark skies, will begin to grow larger in apparent size as the distance decreases. By 3.75 billion years from now, Andromeda will be visible as a large, bright ellipse covering a significant portion of the sky. The first close approach of the two galaxies, the point at which the tidal forces between them begin to strongly distort both disks, occurs at approximately 3.9 billion years. The two galaxies do not simply merge at this point. Their relative velocity is still high enough that they pass through each other. The stars of Andromeda move through the stars of the Milky Way without colliding and continue out the other side. After the first pass, the two galaxies recede from each other but are gravitationally bound. They cannot escape each other. Gravity pulls them back together. The second close approach occurs approximately 500 million years after the first, approximately 4.4 billion years from now. After the second pass, the merger enters its final phase. The two galactic nuclei, each dominated by a supermassive black hole surrounded by a dense concentration of stars, spiral toward each other under dynamical friction. Over the following hundreds of millions of years, they sink toward the center of the combined gravitational potential and eventually merge. The final merged galaxy, the combined system of the Milky Way and Andromeda, is expected to be an elliptical galaxy, not a spiral. Both the Milky Way and Andromeda are spiral galaxies, with ordered rotating disk structures. The violent disturbances of the merger destroy the ordered rotation. Stars that were in circular orbits in the disk are flung into random orientations. The resulting system has a roughly ellipsoidal distribution of stars with random orbital orientations, an elliptical galaxy. This merged galaxy, sometimes called Milkomeda or Milkdromeda in popular accounts, though it has no official designation, will be the dominant galaxy of what remains of the local group after the expansion of space has carried all other galaxy groups beyond the cosmological horizon. The merger will be complete approximately 6 to 7 billion years from now. The Sun will be a white dwarf by then, having exhausted its fuel approximately 5 billion years from now and gone through its red giant phase. The timeline of the Milky Way-Andromeda merger was determined by Cox and Loeb, 2008, and refined by van der Merel et al., 2012, using Hubble Space Telescope proper motion measurements of Andromeda's transverse velocity. The 2012 science paper by van der Merel and colleagues provided the first direct measurement of Andromeda's transverse motion, finding it to be small enough that a head-on or near head-on collision is most likely. The 4.5 billion year timeline represents the most probable first paracenter passage. The Gaia Space Telescope's subsequent measurements of Andromeda's proper motion have further refined these estimates. If the stars do not collide, what actually happens to them during the merger? 3 things. They are ejected, they are redistributed, and new ones are formed. The ejection of stars is one of the most dramatic visible effects of galaxy mergers. During the first close pass, the tidal forces between the two galaxies, the difference in gravitational pull between the near and far sides of each galaxy, stretch the stellar distribution. Stars on the outer edges of each galaxy feel a stronger gravitational pull toward the other galaxy than stars in the interior. This differential pull tears off long streams of stars, called tidal tails, that extend for hundreds of thousands of light years into intergalactic space. These tidal tails are visible in merging galaxy systems throughout the observable universe. The antenna galaxies, NGC 4038 and NGC 4039, two spiral galaxies in the process of merging approximately 45 million light-years from Earth, are among the most studied examples. Their two extended tidal tails stretch for approximately 100,000 light-years, containing hundreds of millions of stars that were torn from the outer disks of each galaxy during their first close pass. The stars in tidal tails are not destroyed. They continue to orbit in the gravitational potential of the merged system. Over billions of years, they fall back into the main body of the merged galaxy, or remain as extended stellar streams, fossil evidence of the merger preserved in the outer halo of the resulting elliptical. Some stars are ejected entirely, given enough energy by the tidal interaction to escape the gravitational potential of the merged system completely. These intergalactic stars, ejected from their home galaxies by the violence of the merger, drift through the void between galaxies, bound to no structure. Current observations suggest that a significant fraction of all stars and galaxy clusters, possibly 10 to 20%, are intergalactic stars ejected by galaxy interactions and mergers over cosmic history. The redistribution of stars is more subtle. The ordered disk structure of a spiral galaxy, with stars in roughly circular orbits in a flat plane, is destroyed by the merger. The gravitational disturbances impart random velocity components to the stars, tilting their orbits out of the plane and introducing radial velocity components. Over hundreds of millions of years, the system relaxes into the random orbit ellipsoidal distribution characteristic of an elliptical galaxy. The formation of new stars is perhaps the most counterintuitive consequence. Galaxy mergers are associated with dramatically elevated rates of star formation, starburst events in which stars form at rates 10 to 100 times higher than in isolated spiral galaxies. The mechanism is the compression of molecular gas clouds during the merger. Spiral galaxies like the Milky Way contain enormous quantities of molecular hydrogen gas, the raw material for star formation. This gas is distributed in clouds throughout the disk. Normally, the gas clouds are in rough equilibrium. The pressure of the interstellar medium prevents them from collapsing under their own gravity. During a merger, the collision of gas clouds from the two galaxies, unlike the stars, the gas does collide because gas has pressure and cannot simply pass through itself, compresses the gas to densities far above the threshold for gravitational collapse. Star formation is triggered on a massive scale. The merged system lights up with thousands of newly forming stars. The antenna galaxies contain over 1,000 star clusters that formed during or after their first close pass, many of them containing hundreds of thousands of stars. The star formation rate in the antenna system is approximately 20 times higher than in a typical isolated spiral galaxy. A galaxy merger is simultaneously a slow-motion gravitational catastrophe and a nursery. The antenna galaxies, NGC 4038/4039, have been the subject of extensive study as the nearest major ongoing galaxy merger, first imaged by Hubble in 1997. The 2010 Whitmore et al. paper in Astronomical Journal identified over 1,000 young star clusters in the system, with ages ranging from a few million to a few billion years, tracing the star formation history of the ongoing merger. The extended tidal tails of the antenna system stretch for approximately 100,000 light-years and contain approximately 10% of the total stellar mass of the system. N-body simulations of the merger, beginning with Tumor and Tumra, 1972, accurately reproduce the observed tidal tail morphology from specific initial orbital parameters. Stop here. The antenna galaxies, the nearest major galaxy merger to Earth, show over 1,000 new star clusters formed during the collision. Star formation rate 20 times higher than normal. Stars being born from the violence of two galaxies crashing through each other. New suns lighting up where chaos is happening. If you could observe the Milky Way Andromeda merger from a safe distance 6 billion years from now, what would you most want to see? Drop your answer below. Now let's address the most personal question about the Milky Way Andromeda merger. What happens to the solar system? The answer is probably not much. And the reasons why are instructive. The solar system is located approximately 26,000 light-years from the center of the Milky Way, roughly halfway out in the galactic disk. During the merger, the orbital distribution of stars will be significantly disturbed. Some stars currently in the disk will be thrown onto highly elliptical orbits. Some will be ejected into the halo. Some will end up in completely different regions of the merged galaxy. The probability that the solar system is ejected entirely, thrown into intergalactic space by the merger, is small but not negligible. Cox and Loeb's 2008 simulation found a probability of approximately 2.7% that the solar system is ejected from the merged galaxy during the merger. A 2.7% chance. Not zero, not negligible, but small. The more interesting question is what happens to the solar system if it remains in the merged galaxy. The orbital distribution of the merged elliptical galaxy is very different from the current disk orbit of the solar system. The Sun currently moves in a roughly circular orbit around the Milky Way's center at approximately 220 kilometers per second, completing one orbit every approximately 225 million years. After the merger, the Sun, if it remains in the merged system, will be on a different orbit. The merger redistributes angular momentum across the stellar population. The Sun's orbit in the merged elliptical could be significantly different from its current orbit, potentially more elliptical, potentially in a completely different plane, potentially passing much closer to or further from the galactic center. The probability of the Sun passing close enough to another star during the merger to significantly perturb the solar system, close enough to alter planetary orbits or eject planets, is approximately 3% according to Cox and Loeb's simulation. 3%. Again, not zero, not likely, but possible. And what about the collision of the two galactic nuclei, the two supermassive black holes, and the star formation burst? These events occur in the dense central regions of the galaxies. The solar system, located in the outer disk at 26,000 light-years from the center, is sufficiently far from the action that the radiation from the starburst and the gravitational wave emission from the black hole merger are unlikely to pose a significant direct threat. The gravitational wave burst from the merger of two supermassive black holes, each with masses of millions to billions of solar masses, will be the most energetic gravitational wave event in the observable universe during that epoch. But at 26,000 light-years from the center, the strain at the solar system's location is calculated to be far too small to produce any observable effects. The most likely outcome for the solar system is survival with orbital modification. The Sun will still exist. It will be a white dwarf by the time the merger completes, but its remnant will still be there. The planets, those that survive the Sun's red giant phase, will still be there, but their position within the merged galaxy will be different from their current position within the Milky Way. The night sky of any hypothetical observer in the solar system 7 billion years from now, assuming any habitable planet still exists, which is unlikely given the sun's evolution, will show the merged elliptical galaxy rather than the spiral arms of the Milky Way. The Milky Way's band across the night sky, the structure of the disk we live in, will no longer be recognizable. The Cox and Loeb 2008 monthly notices of the Royal Astronomical Society paper, The Collision Between the Milky Way and Andromeda, used N-body simulations with 3 million particles to model the merger, tracking the orbital evolution of test particles representing the solar system throughout the process. The simulations found that 12% of solar system-like test particles ended up beyond 50 kiloparsecs from the new galactic center after the merger, in the extended halo, and 2.7% were ejected entirely. The paper is the primary reference for the fate of the solar system during the merger and has been widely cited in both technical and popular accounts. The most energetically extreme event in the Milky Way-Andromeda merger is not the distortion of the galactic disks. It is not the starburst. It is not even the redistribution of stars. It is the merger of the two supermassive black holes. The Milky Way's central black hole, Sagittarius A star, has a mass of approximately 4 million solar masses. Andromeda's central black hole, M31 star, has a mass of approximately 100 million solar masses. Both of these objects are currently quiescent. They are not actively accreting significant amounts of material, and they are not producing quasar-level luminosities. During the galaxy merger, as the two galactic nuclei approach each other and eventually come together, the two supermassive black holes will find themselves in the same region of space, but they will not merge immediately. A single black hole merger requires a mechanism to bring the two black holes close enough for gravitational wave emission to carry away the remaining angular momentum and drive them together. The process is called the final parsec problem. Dynamical friction, the gravitational drag of surrounding stars on the black holes, efficiently brings the two black holes together from large separations to approximately 1 parsec, about 3 light-years, from each other. At that point, dynamical friction becomes inefficient because the black holes have ejected most of the stars that were on the orbits that would allow efficient energy transfer. For the two black holes to merge from 1 parsec, they need to lose more orbital energy. The mechanisms available include the slingshot ejection of stars on orbits that bring them close to both black holes, the interaction with a massive gas disk around one or both black holes, the gravitational wave emission at the reduced separation, and possibly the perturbation of the binary by a third massive object. The final parsec problem is an active area of research. Observations of pairs of supermassive black holes in merging galaxies, including systems like OJ287, a binary black hole system with an orbital period of approximately 12 years and a combined mass of approximately 18 billion solar masses, provide evidence that supermassive black hole binaries do eventually merge. The mechanisms that get them through the final parsec are not fully understood. When the two black holes do merge, over a timescale that may be hundreds of millions to billions of years after the first galactic close pass, the merger will produce the most energetic gravitational wave event that has occurred in the universe since the earliest epochs of cosmic history. The mass of the resulting black hole will be approximately 104 million solar masses, slightly less than the sum of the two, because some mass is radiated away as gravitational waves. The gravitational wave burst at the moment of merger will be detectable by any sufficiently sensitive instrument in the observable universe at the time. LISA, the Laser Interferometer Space Antenna, a planned European Space Agency gravitational wave detector consisting of 3 spacecraft in a triangular configuration with arm lengths of 2.5 million kilometers, is designed specifically to detect the gravitational waves from supermassive black hole mergers. If LISA launches and operates as planned, it will detect the merger of supermassive black holes in other galaxies during its operational lifetime. The Milky Way Andromeda merger will produce the grandest version of this event, a supermassive black hole merger in our own galaxy, 4.5 to 7 billion years from now. No instrument currently in existence will observe it, but the physics will be the same physics that LISA will detect in more distant and more immediate mergers. The final parsec problem was identified as a major theoretical challenge by Milosavljevic and Merritt in a 2003 Astrophysical Journal paper. The problem arises because the loss cone, the set of stellar orbits that allow efficient energy transfer to the black hole binary, is depleted faster than it can be replenished by two-body relaxation, stalling the binary at approximately 1 parsec. Solutions involving triaxial galaxy potentials, massive perturbers, and gas disk interactions have been proposed. The observation of OJ-287's orbital decay, consistent with gravitational wave emission, provides evidence that the final parsec problem is solved in real systems, even if the theoretical mechanism remains debated. Let's follow the story to its conclusion. The merged galaxy, the elliptical that results from the Milky Way Andromeda merger, will be the dominant structure in what remains of the local group. The local group, the collection of approximately 50 galaxies that includes the Milky Way, Andromeda, the Triangulum galaxy, and dozens of smaller satellite galaxies, is gravitationally bound. The expansion of space will eventually carry all galaxies beyond the local group outside the cosmological horizon, but the local group itself will remain bound. Over the billions of years following the Milky Way-Andromeda merger, the other significant galaxy in the local group, the Triangulum galaxy, M33, at approximately 2.7 million light-years from the Milky Way, will also be incorporated into the merged system. Triangulum has a mass of approximately 10% of the Milky Way and will merge with the already combined Milky Way-Andromeda system on a timescale of several billion years after the main merger. The smaller satellite galaxies, the Magellanic Clouds, the dwarf galaxies orbiting both the Milky Way and Andromeda, will also eventually be absorbed. The Large Magellanic Cloud may actually collide with the Milky Way before the Andromeda merger. Simulations suggest it could merge with the Milky Way in approximately 2.4 billion years, earlier than the Andromeda encounter. The end state, the final merged galaxy containing the stellar populations of the Milky Way, Andromeda, Triangulum, and all the satellite galaxies, will be a giant elliptical galaxy, isolated in an increasingly empty universe as the expansion of space carries all other galaxies beyond the horizon. This final elliptical will not be forming new stars. The gas that fueled star formation will have been largely consumed in the merger starburst, converted into stars that have since lived and died. The stellar population of the merged galaxy will be aging, the most massive and luminous stars burning out first, leaving an increasingly red and dim population of lower mass, longer-lived stars. Over tens of billions of years, the stellar population dims. The most massive stars die as neutron stars and black holes within millions of years of the merger. Intermediate mass stars, like the Sun, die as white dwarfs over billions of years. The lowest mass red dwarf stars will burn for trillions of years, long after the merger is complete, long after the universe has entered the epoch of stellar death described in the video on heat death. In the very long term, beyond the timescale of stellar evolution, the merged elliptical will become a system of stellar remnants, white dwarfs, neutron stars, and black holes orbiting the central supermassive black hole in a system that is gradually losing mass through dynamical processes. This is the ultimate fate of the Milky Way. Not a violent end, not a catastrophic destruction. A slow transformation through merger, through star formation and stellar death, through the gradual dimming of a stellar population, into something unrecognizable from what it is today. The galaxy you live in will become something that no longer has spiral arms, no longer forms new stars, no longer looks like a galaxy as we currently understand the term. But it will still be there. Every star that survived the merger, every white dwarf, every neutron star, all of them still orbiting the same central mass, in the same gravitational potential, the same matter, a different shape, a different story. Two galaxies are going to collide. 2 trillion stars, combined, will interact gravitationally over hundreds of millions of years. Tidal tails will stretch for 100,000 light-years into intergalactic space. Star formation will accelerate by a factor of 20. 2 supermassive black holes will spiral together and merge in an event that produces gravitational waves detectable across the observable universe. And almost certainly, not a single star will touch another star. The collision is real. The merger is real. The transformation of 2 spiral galaxies into a single elliptical is real. But the mechanism is not impact, not contact, not the collision of physical objects in the ordinary sense. It is gravity, operating at distances of light years, reshaping the distribution of hundreds of billions of stars over timescales of hundreds of millions of years. Silent, invisible at human scales, inexorable. The solar system will survive, with high probability. It will be in a different part of the merged galaxy. The night sky will be different. The Milky Way's band will be gone. The merged elliptical's diffuse glow will replace it. But the Earth, if it still exists, which it will not, having been consumed by the Sun's red giant phase approximately 500 million years before the merger completes, the Earth would not experience anything dramatic on any human timescale during the merger. The merger takes hundreds of millions of years. On any human timescale, the sky would look almost identical to today's sky. The catastrophe is real. The timescale makes it invisible. In 4.5 billion years, the night sky will begin to change. In 6 billion years, it will be unrecognizable. In 7 billion years, the merger will be complete. It is already gravitationally inevitable. The approach has been underway since the Big Bang. Andromeda has been falling toward the Milky Way for 13.8 billion years. It is coming. We just cannot see it moving. One question. In 4.5 billion years, Andromeda will be visible in the night sky as a structure covering a significant portion of the sky, brighter than the Milky Way band is today. If you could observe that sky 4 billion years from now, before the first close pass, what would you most want to understand about what you were seeing? Not to change it, not to survive it, just to understand it. Drop your answer below. Next video, what happens to Earth if the moon disappeared tonight? Why the moon is responsible for the stability of Earth's axial tilt. What happens to the seasons, the tides, the length of the day, and the long-term climate when the stabilizing influence of the moon is removed? And the detail that most people do not know, that the moon is slowly moving away from Earth, and what that means on geological timescales.
See you there.